So the topic for today is iterations in base R. Okay, so when I say iterations, I basically mean loops, right? Anytime you're iterating over something, you're doing the same thing to something over and over again. All right, so we're gonna look at iterations, and then we're gonna have lab 1. Okay, so we're gonna start out by looking at what I would say is the most basic sort of loop that you can do, which is a for loop. Okay, and then and the thing that is nice about for loops is they are pretty language agnostic. Okay, if you write a for loop in R, you can write a for loop in Python, you can write a for loop in whatever. They're pretty much the exact same across programming languages. But then from there, we'll dig into these more R specific variants, which are this apply family of loops. There's other apply family loops, specifically apply at bottom, that we will only cover very briefly. We'll mostly focus on lapply, and then sapply and vapply are basically the same thing, just with slight differences. Okay, and then after that, we will have our first lab for the term. Okay, so learning objectives for today: understand the basics of what it means to loop through a vector. Okay, so you have some vector of values, and then you want to loop through that vector and either use those as arguments in a function or apply some function to each element of the vector, usually. Okay, hopefully you will begin to recognize use cases. That'll actually probably come more as we continue on with the term. One of the things that's really nice about the tidyverse is that it makes it so we don't have to write loops a lot of the time. And so sometimes it will not be exactly clear why we would write a for loop or any other kind of loop, because there's tidyverse ways of doing it. All right. But I will say a couple of different things. I would feel like a bit of a fraud if I had you all go through 4 to 5 courses, 4 courses in a capstone of data science courses, and you didn't know how to write a for loop, right? They're very important for programming. But B, all the tidyverse stuff works on data frames only. And when you're programming, you're writing new functions, it's very regular that you're wanting to do something to a vector rather than an entire data frame. Like, you don't always want to have to be working with data frames, in part because like sometimes it's super nice to still program with data frames, but it can also be sort of a lot of overhead for something that's a pretty simple operation. So you can end up with potentially having much slower code because you're working in data frames than if you just loop through a vector. Okay, so we'll hopefully by the end of the day you'll be able to apply for loops and understand and be able to apply their equivalents with at least lapply, and we'll look at some of the others too. Okay, so this is the basic anatomy of a for loop. You say for, right, and then you have some index here. I is just sort of convention. People use I for the first index, then J, then K, etc. But it can be anything. Okay, and so very regularly people will use full words there for the index, and so it doesn't have to be I. There's nothing special about I, right? So for example, let's say you have a vector of colors that you want to loop through, then you might say for color in colors, right, where colors is the vector that you're looping through. But you could also just as easily say for I in colors, right? So I is just sort of convention, but it can be anything. Then you say for I in, or for whatever in, you always have this in, then you put the vector that you want to loop through. Okay, so sometimes it's just indexes like this, because you're going to use that as to index the thing that you're looping through, but very regularly it's also just a vector on its own. Like I said before, you could just loop through colors, right? And then you'd say print, and then you're going to in this case, we're printing each element of some vector A each time. Okay, so let's look at how this actually works. This is the for loop for what we're going to do here. And you can feel free to follow along. I'm not going to move super fast through this first part, so you should be able to follow along pretty easily, but you don't have to if you don't want. You can just watch. Okay, in base R, there is letters undercase, lowercase, and letters all uppercase. And those are just built-in vectors that have the letters of the alphabet. Okay, so if I say letters 1 to 26, I get all of them. I don't really have to have the 1 to 26 there. I don't know why I did. But you could also do, 1 to 10, and you'd get the first 10 letters or whatever. So here's A, which is just our letters. When I do this loop that I had before for I in 1 to 5, it's going to go through here and it's going to print the first element. Then it's going to print the second element. Then it's going to print the third element. Why is it doing that? Because that's what we have in our index here. 1, 2, 3, 4, 5. And then we're indexing this here. Okay, so we're using the single brackets because this is a vector, not a list. And so we're saying print A1, print A2, print A3, etc. Okay, and we get this in return. So notice that in this case, it looks pretty similar, except it's all stacking vertically instead of horizontally. But it's very different, actually, because in the top part, we have a single vector that's of length 26, right? In the lower part, we have 5 vectors, each of length 1. Okay, so these are really different things, even though they look pretty similar. All right, so let's think about creating indexes. Very commonly, you will see code like this, and it will be very, you'll probably want to write code like this a lot of the time, where you have from 1 colon to something, right, to the number of rows in the data frame or the number of columns in the data frame. Okay, instead, I would encourage you to avoid this. Okay, this is not like the biggest deal in the world, but it is a way to improve your code and make it less buggy, as I'll show in just a second. So instead of saying 1 colon and then some calculation of a length, you would instead just use seek along or seek length. Okay, seek length. And the reason is because, so these functions work like this, right? Here I have this vector x, and I say seek along. It's just going to find that vector x, and it's going to create an index from 1 to however long that vector is. Okay, that's what seek along does. It creates a sequence along the vector that you're going to be indexing. Okay, seek length works the same way, except instead of feeding it a vector, you just feed it a single value. So in this case, I'm using length of x. Okay, and so it's just a single integer value, and here I'm first calculating the length of x, and then I'm feeding that to seek length, and it's going to, so this simplifies to seek length 3, and then it's just going to create an index from 1 to 3. Okay, so why am I advocating for the use of these instead of that 1 colon calculation rule, right? Again, not the biggest deal, but it is going to help you write cleaner code that's less buggy, because we can end up with things like this. Okay, so here I have some empty vector, which I'm calling means, right? Means is of length 0, right? So when I say 1 to the length of means, this is actually creating an index that goes 1 to 0. Okay, so you're going backwards from 1 to 0. And so then you get this error because it doesn't work, right? Instead, if you use the seek version, then it's not going to create that index because there is no length for it to create the sequence from. So then the loop is just not executed. Okay, that also, if you're writing functions, having this loop not execute may introduce bugs further down the line. So ideally, you would want to have some check for this first but this is going to generally be a safer version than the prior version, okay? And often when you get these sorts of errors, they're going to be tough to debug because you get something like this, invalid arguments, right? And it's not super clear what the invalid argument is, why that's happening, okay? So again, not the biggest deal, but something to consider. All right. Another basic example. So let's write another for loop. And this time, we're going to simulate tossing a coin. Okay, there are ways to do this in a vectorized way, so we don't actually have to write loops for it, but we're going to ignore that for a minute. Okay, so this is how I would do it for a single toss. I'm going to sample from some vector that has two things in it, heads or tails, right? And I'm going to sample one time. When I do that, in this case, I get heads, but I could get heads or tails, right? If I wanted to do this 10 times, right? I'm going to simulate tossing this coin 10 times. What I want to do before I actually write my for loop is pre-allocate a vector, okay? So here I'm creating an empty vector, which is called result, and it's just a vector of length 10 that all has NAs, okay? Then when I go to write my actual loop, you will see I'm doing that same sample code, right? Oops. I'm doing this same sample code. There's nothing different about this, but I am storing it into the ith element of results, okay? And that I is from seek along result, okay? So that seek along is going to give me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then this is going to store the result in the ith element. And we get tails, heads, tails, heads, tails, 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 heads, etc. Okay? Any questions on that? So the process here, I think, is relatively straightforward. But what can get tricky about for loops for sure, and this is part of why the base version will be preferred, the other apply versions, is that it's just a lot of code to write for a single loop, okay? And so figuring out, like in this case, there's actually nothing on this side that I need to index, and that's kind of unusual, right? So figuring out that, and then where does this go? Is it single brackets? Is it double brackets? Getting your index right up here. All of that stuff can be a little tricky if you're not used to writing loops. Okay. In the previous example, I pre-allocated that vector, right? So I created an empty vector that just had basically spots where I was going to fill in the results as it went along, right? The reason I did that is because I wanted to avoid what's called growing vectors, okay? And I am very strongly advocating that you always do that, okay? Anytime you ever write a for loop, you should always pre-allocate the vector. Okay, it will work. Otherwise, if you just grow the vector, as I'll show you an example in a second, it will absolutely work. However, it will be dramatically slower. Okay, so you will see things on the internet, on Stack Overflow or whatever, about how base R for loops are slow and they should be avoided because they're slow. That's wrong. It's just straight up wrong. For loops are not any slower than lapply or any of the other loops. They are actually basically equivalent. The difference is when people are not pre-allocating their vectors, then the for loop can be very, very slow. Okay, yes. So that pre-allocating a vector is this part. Okay, so before I run the loop, I create this result object that has NAs padded for where I'm going to fill in my results. So then all the slots that the results are going to go into are already created, right? And the reason that this ends up working so much better is because then you're just doing the result and storing it, versus if you're growing the vector, so you're on the third element and then that vector becomes of length 4, and then the next time it becomes length 5. Every time you're having to basically reallocate the vector. Okay, So let's look at an example here. Okay. I'm using this library here called TikTok. It's just a really easy way to get timings on things. And so I'm setting a seed so it'll be reproducible. I say tick, and then my code, and then I say talk, and it gives me the time that it took to run that code. Okay. So I'm starting here by growing a vector. Okay, writing the for loop in a way where the vector is not pre-allocated and it just continues to grow. So right here, right, I'm creating a thing that I'm calling not allocated. And all this is one draw from that sample, right? And then when I run my loop, notice I'm doing 100,000 draws. I'm saying 100,000 minus 1 because I've already got 1 up here, right? This is the first one. And then I'm just using C to combine the results of not allocated and the next sample, okay? So right here at this line of code, the not allocated vector is of length 1. After the first iteration, it will be of length 2. Then it will be of length 3, then 4, all the way up to 100,000, okay? When I write the code this way, so I'm growing the vector, it takes 50 seconds to do this. Okay, this is a pretty simple operation. We're just sampling heads or tails, but we're doing it 100,000 times, and so it takes about 50 seconds. By contrast, if I pre-allocate that vector first, and I just say allocated rep NA 100,000 times, right? And then I'm just filling in each of those with my sample, the whole thing runs in less than a second. Okay, so that is a ridiculous difference, right? And again, this is a very, very simple operation. Okay, it is like a little bit big, you know, 100,000 iterations is fairly large for anything, but the actual operation is very, very simple. Okay, so you can imagine if you were doing something much more complicated, that this could result in huge differences in the performance of your loops. Okay, any questions on that? Yep. You should pretty much always know for a for loop. So there's different kinds of loops, but for a for loop, you should always have something that you're looping through. And so then the end result should be the same length as that. Right? Do you have a idea of like one way?
Running a for loop, and I mean, I'm just thinking it's not like a standalone for loop, but like within some function or something that I check the condition and then.
Yes. So in those examples where you're having to check a condition, you would just pre-allocate it to the like max condition, and then each time it went through, if that wasn't true, it would probably just be filled with NAs, and then at the end you could just remove the NAs or whatever. Okay, we can also see, because I set the seed on these, that the results of these two things are exactly identical, right? If I call identical on not allocated and allocated, I get true. Okay, so the result that we get is exactly the same, but speed is obviously not the same. Okay, so that's a very quick introduction to for loops. But what I'd like to do, I've set aside 3 minutes here. We can go longer if we need to. I'm happy that many of you are in person because I can walk around and kind of see where you're at. So I'm going to start us out with 3 minutes. If we need more time, we can. Okay. But what I'd like you to do is try to write a for loop where you're using both letters lowercase and letters uppercase to combine them into basically like an elementary school alphabet, right? So it's like uppercase A, lowercase a, uppercase B, lowercase b. Okay. So this is the code that you would do it for one of them, right? For A, that would get you AA, just like that. So what I'd like you to do is try to extend that code so that you're applying it for all letters. Make sense? Okay, so we'll start out with 3 minutes and see where we're at. Okay, that's 3 minutes. Do you want another minute or are you feeling okay? Good? Okay. All right, looks like most people are saying yes. Let's continue. Okay, so this is how I did it. I first pre-allocated my vector. I called it alphabet. You can call it whatever you want to call it, obviously. And I'm just going to repeat NA the length of letters. Okay. Then I'm going to say for I in seek along alphabet, this thing I just created, right? I'm going to paste letters I with letters I, uppercase with lowercase, right? And that's going to be stored in the ith element of alphabet. Okay. And then we look at that and we get our upper and lowercase versions. Make sense? Any questions? Okay, good. All right, so another example. There's a fair amount of simulation-based stuff that I do through these slides. So if that's not something that you're really comfortable with or familiar with, that's totally okay, right? This is just for an example, all right? But let's say that we wanted to simulate 100 cases, so 100 observations from a random normal distribution, okay? So in R, you can do that with the R norm function. So it's going to assume a normal distribution, and you're going to randomly draw cases from that. But that normal distribution has some parameters, right? Like the mean and the standard deviation. So where it's like the center point is basically, and then how broad it is, right? And so we're going to simulate 100 observations from that random normal distribution where we vary the standard deviation in increments of 0.2, okay? So we're just gonna, I think we're just assuming the mean is 0. And we'll say the standard deviation is 1, 1.2, 1.4, 1.6. And for each of those different variances, standard deviations, we're going to draw 100 observations. Okay? So, as I just said, hopefully this is relatable, but if not, it's okay. Just kind of focus on the process of what's actually going on. Okay? So first, the way that I would do this is instead of pre-allocating a vector, I mean, I actually will do that too, but the first thing I'm going to do is create my sequence of standard deviations. Okay, so I probably should have called this like SDS for standard deviations, but instead I just called it increments. So like the increments that we're going up as we're changing the standard deviation. So this is a sequence from 1 to 5 by 0.2. Okay, exactly what we set up here. Okay, next we need to pre-allocate our vector. And in this case, because I'm pulling 100 observations, I can't just do an atomic vector, right? Like we did last time. So I could use a couple of different things. I could use a data frame or a matrix where I have the observations as rows or columns, and then the iterations as the other one, right? But I think actually most simple is to use a list, okay? So what I'll do then is I'm creating an empty list, and there's a couple of different ways that you can do this, but this is, I think, the most straightforward way. I'm saying I want to create a vector of type list, okay? And I want the length of that vector to be the same length as increments, okay? So let's look at what simulated looks like now. Notice it's a list of 21, and it's just a bunch of nulls, okay? Now what we want to do is we want to fill in each of those with our 100 draws from the random normal distribution with the corresponding standard deviation, okay? So we're going to do it like this. For I in seek along simulated, okay? And notice again, simulated is here. It's a list of 21. When I do seek along, it's going to understand that that thing is 21. And so it's going to go 1, 2, 3, 4, 5. So it doesn't have to be an atomic vector to do that, right? It can be a list vector as well. And then I'm going to say fill in the ith element of simulated with R norm of 100 with a mean of 0 and a standard deviation of increments I. Okay, I want you to notice here though, we talked about this last class, and it's very important, when I'm indexing increments with I, right, I'm just using single brackets. When I'm doing simulated, I'm using double brackets. Why? Do we remember? Say that a little louder. Okay. So the reason is because we're we're trying to store it into a list, right? And lists, you can use single brackets or double brackets. The single bracket is going to return a list, right? So I could say from this simulated, give me the third through the fifth elements, and it would return a list with these elements, right? But if I wanted to say, okay, give me the contents of one of the elements of the list, like give me what's inside this first one, then I would use double brackets, okay? So in this case, we're not pulling what's inside of it, we're storing something to it, okay? And so we have to say, go inside the list. Remember that analogy we used with like train cars, right? There's like the train and then the box cars. So this is like the double brackets is saying like go inside one of the box cars, and in this case, put something in there, right? Whereas the single brackets are saying, give me the actual box cars back. Okay. So when I do that, it works like this. We get our 100 observations from each of them. And that's all good. Now that we have that though, remember we talked about last time that a data frame is just a special kind of list, right? And if you have a list where all of the elements of the list are the same length, right? Then you can transform it to a data frame very easily. So in this case, I wanted to first give it a little bit more meaningful names. So I'm saying the names of simulated, if we go back here, right? They don't have names right now. There are no names for this list. So I'm saying paste together SD underscore with increments, right? And I'm saving that as the names. So the names are now standard deviation 1, standard deviation 1.2, standard deviation 1.4, etc. Now, yep.
How does it know what the column names are if there's a column name?
Yeah, so there are no column names. I'm creating them right here. So remember when I created that increments thing back here? Increments looks like this, right? And so then I created the vector and there are no names, right? But we know that this thing, this simulated thing, is the same length as increments because that's how we created it here, right? We said create a vector of type list that's the length of increments. So we know that this is going to be the same length as this. So when I call over here, when I say the names of simulated, that's going to return 21 nulls, right? It would actually probably just return one null, but regardless, here, now I'm just pasting together SD and increments. So this is a vector that just says SD1, SD1.2, SD1.4. And so then I'm saying, okay, now assign the names of simulated to this, right? And then that gives me all of these. Does that make sense? Good. Okay, so now that these have meaningful names, I can transform it to a data frame very easily. I just wrap data.frame around it. Okay, and I get a data frame that looks like this. If I wanted to then plot these using the tidyverse would be the best way to do this, probably, right? So I'm pivoting longer, everything, and then I'm saying the names are going to go to SD and the values are going to go to sim, and then I'm wiping up the SD underscore part, and then I'm saying SD is going to be a factor, all right? So this is like pivoting the whole data longer, and then at that point, I can create the plot very easily by just saying the color is equal to the standard deviation. Okay, I omitted I probably should have said group instead of color, because as we talked about in last class, This is way too many colors to actually distinguish it, right? What each one is, and that's why I just removed the guide altogether. But regardless, so this is really nice though, right? We get all of the density curves for all of these. And what's interesting is that this is a very good example of where the tidyverse sort of, by doing a little bit of data manipulation first, gets us out of doing any sort of looping on our own to create this plot, right? If we didn't have the tidyverse, then we would have to write the loops ourselves, right? So this is a quote by Jenny Bryan that I've liked forever. Somebody has to write loops, right? Doesn't have to be you necessarily, somebody does. So let's go ahead, because we're talking about writing loops, and do the looping ourselves, okay? I'm gonna do this with base R. And again, as I'm going through this, I very much expect that this is feeling kind of fast and that, you know, it's easy to follow along, but not so easy to like write the code on your own, right? This is your, for most of you anyway, not all of you, this is your first introduction to looping like this and even thinking in this sort of a way. So if this feels like overwhelming, that's okay, right? We're just getting started here, and it's a lot of new stuff really fast. That's why we're gonna have time to practice during the lab, and I'll have a few more practice sessions as we go through here, okay? All right, so if we wanted to do this with base looping, we would start by saying, okay, well, we need to calculate all the densities. Because if I go back here, right, each of these is a density plot. So we need to calculate the actual density for each of them, okay? So that's the first step. So I'm going to use a list again, and I'm going to use this density function, okay? This is like basically fitting a model, right? And so I'm going to say for seek-along densities, this list, right? Density, double bracket I, right? Fill in each element of that densities thing with the actual estimated density of SimDF. Notice I'm going all rows for the ith column, okay? And that's because our data looks like this, right? So I'm saying basically when I'm looping through on that slide I just showed, give me the density of this column, give me the density of this column, give me the density of this column, right? And it's looping through each column. So that's what we're at here, all rows for the ith column, okay? And SIMD, the length of SIMD is, it's a data frame at this point, but a data frame is a list, right? So if you think about abstracting away from the data frame, the length of a data frame is going to be equal to the number of columns of the data frame, okay? All right, so that gives me all of my densities. And again, I know this is super fast. I really don't care about densities for this whole side of things. So that's part of why I'm moving fast. But next we would plot the first density, right? So we just say plot densities, double bracket 1, we get the first density. Then if we wanted to plot the rest of the densities, we could use this lines function. This is base R plotting stuff, okay? But now I'm saying for a sequence from the second observation, because we already did the first one up here, through the length of densities, give me a line where x is equal to densities double bracket I x, and the y is equal to densities double bracket I y. Okay, and that plots all of them. Okay. So this is, again, this is like a lot for just introducing for loops. And this is, if I were to do this for real, right, I would probably have done the simulation part fairly similar to how I just showed it. However, for the plotting, I would have done it the ggplot way, right? I wouldn't go to this sort of looping for this, but it is, this is essentially, although in the tidyverse world, right, this is essentially what is happening when you're doing it in ggplot. Okay. All right. You can also skip iterations. So very regularly, you do things like this, where you say a sequence from the second one onwards, right? But you can also do something like this, where you say if I equal 1, next, okay? And so what that's going to do is it's just going to skip that iteration. So in this case, the if I equal 1 is kind of silly. Normally, you wouldn't really do that. What you would probably do is, I mean, you could if it was something like this, but most of the time that you're using a next, it's for something like you're doing some calculation and it assumes that it's positive. And so then you have to say if whatever the thing is negative, then next. Like just skip that one and go on. Okay. This is not something I use a whole lot of though, because I usually get that figured out before I'm doing my looping. You can also break loops. This is not usually as important for loops as it is for other types of loops. We will not really talk about many other types of loops in this class, but there are loops like while loops, for example, that are often used for optimization, right? So you're saying like, while some value is greater than some threshold, keep iterating. And it's just going to keep iterating until that condition is met. Okay. And so for a while loop, you have to have an explicit break. Okay. Because, or you don't have to, but you usually want to, because otherwise you can get in these situations where you have an infinite loop that will just run on forever and ever and ever and ever and ever until you close down your computer. Okay. Or close down the program at least. But the way that you stop loops generally, whether it's a for loop or a while loop or anything else, is with break. Okay, so this is a very simple, silly example that isn't really very real, right? But saying, okay, simulate data from a random uniform distribution, and I'm going to say for I in seek along that thing. So notice I'm using that same vector code in this one, but I'm saying give me a vector of type double where the length is 10. Okay, this is just another way of doing like rep NA 10 times, basically. But it's just assuring that it's type double. So then I'm going to say rand unif I get simulate from a random uniform distribution, one observation, somewhere between 0 and 10 on that uniform distribution. And then I'm saying if any of those are greater than 5, break. Okay, and so you can see, because I use set seed 1, this should be replicable for you, but you could try playing with a different seed and see how it works, right? So it works the first time, works the second time, works the third time, but then it's checking after this, after each time it's checking to see if any are greater than 5. For me, this third one was greater than 5, so it breaks. And now the loop stops and the rest of the vector are just the zeros that were there previously by creating it like this. Okay? Any questions on that? All right. So that's the for loop family. The ending of that, I think, in particular, is less important. The most important is the parts that I said at the beginning, right? So you don't always have to have I. It could be called anything that you want it to be, anything that makes the most sense for you. So for example, it's very common that you'll see somebody looping through rows and they'll say for row in, something. And then when they get through there, they're saying row, comma, and then whatever column it is. Or if they're looping through columns, they'll say for call in like COL, right? So that's one thing. So like just big things to keep in mind. It doesn't have to be I, it could be anything that makes it clearer. Always pre-allocate the vector, okay? And then generally from there, the rest should just follow that same general formula, right? It's like a recipe for whatever for sequence or for whatever indicator in some sequence, do the thing, and then output. Okay, the breaking and the skipping and all of that stuff is not nearly as big of a deal. Okay. All right. The last thing I'll say too, though, about for loops is the same thing that I've said about other loops, but with for loops in particular, people will go pretty deep on them. So they'll go for I in, and then you'll get inside of that one, and it's for j in, and then you'll get inside of that one, and then they're looping through I and j, and then sometimes even within that for k in, and then it's I, j, k. I would really strongly recommend against that. It becomes super complicated to track. You can, but it's not easy, not fun. So instead, what we're going to do is pull out a level. Okay. So your innermost level that is looping through, you can just take all of that and you can wrap it in a function. Okay. And then you can say for I in, and then you can just call that function, which does the other loop, but you don't have to think about it when you're writing the outer loop. Okay. So I know we haven't talked about writing functions yet. We'll do that more later in the term, but pretty much always, I would say, if you're getting into nested loops, there's better ways to do it. Okay. All right. Any questions on for loops before we jump forward here? Okay. So the apply family. lapply is to me the most important of the apply family of loops. Okay. It is one of numerous what Hadley calls functionals. Okay. And so a functional, I say Hadley calls it that because he's the only one I've ever heard call it that. Doesn't mean that that's not actually what it's called, but that's the only place I've seen it. Okay. So a functional takes a function as an input and returns a vector as its output. Okay. But you also, this to me is a little bit confusing because it does take a function as its input, but you also have to have the vector that you're going to apply that function to. So it kind of takes both of them. Okay. lapply will always, always, always return a list. Okay. And so that's where the L in lapply comes from. The first L, right? For list output. Okay. That makes lapply very safe. It's very type safe. You always know every single time you apply lapply that you're going to get a list as a list return. Okay. So let's revisit for a second our simulation that we did with n equals 10. Okay, so our for loop version looked like this. We had increments 1 to 5 by 0.2, and then we pre-allocated our vector, which we're calling simulated, where it's of type list, and it's going to be the length of increments, right? And then we actually get to the point where we're running our for loop, and we say for I in seek along simulated, simulated double bracket I. So we're filling in each of those things. We're pulling from a random normal distribution where n is equal to 10, the mean is equal to 0, and the increments are the standard deviation is the ith increment, right? And then we get our simulated thing down here. Okay, so that's fine. That works, right? It's 1, 2, 3, 4 lines of code, basically. Five lines of code. Okay. But the lapply version is really 1 line of code, and but I've broken it apart in 2 lines here. The lapply version, we just say lapply increments. Okay, increments is the thing that we're going to loop over, and then we tell it the function that we want it to apply. In this case, we're applying what's called an anonymous function. Okay, it's anonymous because it's not bound to a name like mean or whatever. So I'm again, this part of this is just like with for loops. What's inside these parentheses here could be anything. Very regularly, like just by convention, it's usually X and then Y and then Z. But it can and should be something more meaningful if it makes sense. So in this case, I'm saying apply a function that takes one argument, which is the standard deviation. Okay, because that's what these increments are, right? They're the different standard deviations that I want to apply. So I'm going to loop through increments and apply this function. Okay, it's a function that takes an argument standard deviation, and then we go R norm 10, 0, SD. Okay, and so this SD gets filled in with each element of increments. Okay, notice when I'm doing this, I do not have to pre-allocate a vector, right? I don't have to do anything other than tell it what I want to loop over and tell it the function that I want it to apply. Okay, and the results are exactly the same. The output is exactly the same. More examples. We could also loop through a data frame, right? So again, as I mentioned earlier, and we'll probably mention many other times throughout this class, a data frame is a list. So we can loop through the data frame very easily, just like we would loop through a list. Okay, so here's a basic example where I'm loading the Palmer Penguins data set, and that has the penguins actual data set, right? And I'm saying lapply penguins. So again, when you're looping through a data frame, it is a list. Each element of the list is a column. Okay, so when you do lapply through penguins, you're really just looping through the columns, which are the elements of the list. Okay, so I'm saying lapply penguins is dot double. So I'm applying one function is dot double. Notice in this case, I'm not saying function call is dot double call, right? I could do that for sure. And in fact, I think I do on the next slide. But if you don't need to do that, you can also just pass it the function that you want it to apply to each element of it. Okay, so species is false, island is false, but bill length and bill depth are true. Okay, those are both double. Flipper length is false, which is interesting. It seems like that should be true, but okay, so is that double call? And then here's another example where I'm looping through the columns of the empty cars data set, and I'm saying, what's the mean, right? So notice we get all of the, just like in the previous example, the elements of the list that are returned are the old column names, okay? So as it's looping through those columns, it pulls the column names for the list. And here's all of the means for empty cars. All right. We could also add a condition. Okay, so, and this I would do fairly frequently. I do fairly frequently. Okay, so now I'm looping through penguins and I'm applying a function x. Okay, again, this can be anything in this function, anything that makes the most sense to you. Okay, but by convention, if there's not like something that really makes a lot of sense to use, just as a shorthand, people use x. Okay, and so that x is just like a placeholder for each iteration of the thing that you're looping through. So in this case, we're looping through penguins, so that x is a placeholder for each column as we're going through. Okay, so in this case, we're saying if is.numeric x, so if the column is numeric, then we're going to compute the mean of x, and we're going to remove missing data. Okay, otherwise we're not going to do anything. That's the only if we have. So for species and island, we just get null returned because this condition was not met. Okay, and because that condition is not met, the mean is not evaluated, and so it essentially just skips over it. Okay, we could instead say do something different with it, right? So in this case, we're saying if it's numeric, then do the mean. Else, if is dot character or is dot factor, and we could probably just say else. We don't really have to do that. But if we had some logical columns, maybe it would make sense. I don't know. Then we're going to return a table. Okay, notice here too, I do have these explicit return statements. So I have return here and return here. Okay. When we get to the point where we're writing functions, you will see a lot you will see at the very end of the function, people will sometimes write return and then put the explicit thing they want it to return. Generally, that's not advisable. You want to save return for these sorts of situations. So this is like an early exit, right? We're going to return this if it's numeric. And so that means we're not going to evaluate anything after that because we've already returned the thing, okay? And we probably don't actually need this return here because that will just happen if this isn't returned, okay? All right. Within lapply, you can also pass additional arguments. So here we have the air quality data set. It has missing data. And so if I say lapply air quality mean, so loop through all the columns and give me the mean of each column, notice we get NA for ozone and we get NA for solar.R because as you can see above, there is missing data on those columns. So what we can do is just pass an additional argument to lapply. Okay, if you look at the documentation for lapply, it will have, in fact, let's just do it real quick. It will have basically some dots and it will have some dots. That's not what I want. And those dots basically will, they basically mean, oh my gosh. They basically mean additional arguments to the function that you're looping through. So hopefully this thing will pull up. My goodness, I'm having issues with my computer today. All right. Okay, so if I go question mark and I say lapply, oops, right over here, you'll see that it's lapply x. X is going to be the vector that you're going to loop over, right? And then fun is the function that you're going to apply to each element of x. And then the last one is just ... right? And this is optional arguments to fun. Okay, so that's what's going on here, is these are additional arguments that are getting passed to the function that's being applied on each iteration. Okay, we could just as easily write the function like this. Okay, so this is clearer to a lot of people. And if that is the case for you, then great, write it like this. Okay, but I want you to at least know that you can just pass the arguments directly to lapply as well. Okay, so this slide and this slide are exactly the same. Yep.
What if there are multiple arguments you want to pass?
You can just continue to pass additional arguments.
Just commas. You don't have
Yep.
to like.
Yeah. So back here, like you would just do comma and then pass the additional arguments. Any other questions? Okay. Let's look at our simulation again. So here I am looping through those different standard deviation values, but I'm applying, so this is exactly what you just asked about, right? I'm applying the function R norm, but then I'm just going and passing additional arguments, n equals 10, mean equals 0, okay? You do generally want to name those arguments when you're passing them through the dots to be sure that they're the actual argument that you want to be evaluated. But otherwise, it should all just work. Okay, questions on anything so far? How are we feeling generally? Okay? All right. Okay, the next thing we're going to talk about is operations by group. Okay, so let's see. This way around. Well, all right. Would you rather take a quick break now and then do that, or should we push through this and then have a longer lab, I guess, by a little bit? Do you want a break or not? I guess is the question. Yes? All right, let's take a break. So it is about 2:00. Let's say we'll be back at 2:10. So 7 minutes. Okay. Okay. Here we go. So we're going to talk about operations by group. Basically, what we're going to do here now is replicate dplyr's group by, right? When you want to do something by group, typically what you have to do is you have to split by that group, apply the operation to each group, and then combine them all back together. Okay, so that's what people refer to Hadley specifically as the split, apply, combine sort of operation. And group by does that all for you without having to think about it. But sometimes you don't want to use group by for numerous reasons, right? Could be because you're not working with the data frame, or it could be because you don't want to use the tidyverse in a function and avoid that dependency, etc. So here's an example. It's a very quick example. But let's say we wanted to go through the empty cars data set and we wanted to apply some operation by cylinder. Okay, so for each unique instance of cylinder, we want to conduct some operation. The first thing we're going to do is we're going to split empty cars by empty cars sil. Okay, so what this is doing is now we have a data frame where the first element of the list, so it returns the list. Notice it says it's a list of length 3, right? The first element of the list is the data frame for only those where the cylinder is 4. Okay? The second element of the list is the data frame where the cylinder is 6. And then the third is the data frame where the cylinder is 8. Okay, so for this first one, for example, these are only the 4-cylinder cars, right? There's no other cars in there. And so this value of sil, which you can see right here, is going to be constant. Okay, it's just going to say 4 all the way across. All right. Notice here too that we have different number of cars in each of them. So this data frame is 11 rows. This second data frame is only 7. Okay, so there are 11 cars in this data set with 4 cylinders and only 7 that are 6 cylinders. Okay, so now we have a list of data frames. Okay, and once we have that list, we can use lapply or a for loop to loop through that and do some operation. Okay, so in this case, I'm saying do this function x, where x is just the placeholder for the data frame. Okay, so maybe instead of x here, I should have had df for data frame, right? And then I'm saying give me the mean of x $MPG. So this is saying extract the MPG column from this data frame and give me the mean of it. Okay, for each of these. Does that make sense? Okay, I will say the $ is a little bit dangerous because sometimes you think you can index with a $ and you actually can't. So it's probably safer to use brackets and then you can use quotes, or you could use an index. All right, what I'd like you to do now is to try to do basically the same thing, but working with a different data set. Okay, so we're going to work with the penguins data set. So I'd like you to load that and then calculate the average bill length by species. Okay, so for every species, return the average bill length. Make sense? Okay, so you got 4 minutes for that. All right, so I want to get just a little bit of formative feedback. So raise your hand and give me like a 5 if you feel super confident in that, like 3 if you're kind of in the middle, and 1 if you're like pretty lost. Okay, great. So Good. What, I guess I was gonna actually demo it. The way I would do this, and there's, a couple of different ways, but mostly it's gonna look like this. Palmer penguins, right? Then we look at penguins, and it looks like this, right? I'm gonna make this bigger. Okay. All right, so it's like this, and we want to split by species first. So I'm going to call it by species. Split penguins by penguins species, right? And then I can look at the structure of that, and you can see, pull this over more, maybe. All right, you can see that we have a list of length 3, just like we had before, where this first factor is for all the adelli, this second one is for all the chin strap, and this last one is for all the gentoo. So this is 124 observations, this one's 68, and this one's 152. All right, so now we wanted to compute the mean bill length, right? So then I would just say lapply by species. I'm going to loop through each of those, and I'm going to say function x, or I could call it df, and then say mean of df bill length millimeters. All right, and that doesn't quite work. We end up with some NAs, right? So I just need to modify this. So to, instead of just computing the mean, adding an additional argument where I'm saying na.rm equals true. And now we get the results that we would expect. Okay, any questions on that? The other thing that we can do is, as we start to write more and more code here for our function, it gets longer and longer, right? So after we write this function part, we can also add, the curly braces like this, and then put this on its own new line, and then close out the curly braces there. Okay, so that's the exact same thing, and that can make it all be a little more readable, because basically what the operation that we're doing is within these curly brackets. The thing that we're looping through is there. Okay. All right, back here we go. Now, let's say that we wanted to compute separate plots. Okay, so here I'm still working with that BySil object, that BySil list, right, of the cars data frame BySil. So what I can do is I can say lapply loop through BySil and apply this function x. Again, it could be df, it could be whatever, and call ggplot on that, where I put disp on the x-axis and mpg on the y-axis, and then call geom_point and geom_smooth. What's neat about this is this immediately then produces 3 separate plots for us, one for each cylinder, right? So what I'd like you to do is do basically the same thing again, but produce separate plots for each species, showing the relation between bill length and body mass. Okay? So I give you 4 minutes for that again, but we may not need the full 4 minutes. We'll see how we're doing. Let's move on. Basically, from there, we can go back to here again. We have by species, right? So we're going to do the same sort of thing, loop through by species, and apply a function to each data frame. And I'm going to say ggplot, and then what did I say, that bill length and body mass. So you're going to put the df in there that you're going to loop through, and then AES bill length millimeters, bill body mass G plus geom smooth plus geom. Yes, so I need to load. Okay, and now this should work. And you can see over here, right, this is for the last one, Adelie, I think. And then there's another one and another one. Okay. So they should look roughly like that. In fact, they should look identical to that, unless you change the theme or whatever. Okay. Any questions on that? Yep.
I guess like as like, let's say the functions get more complicated, would it be possible to let's say do like a function and make it separately?
Yes. So like basically we could do something like this, right? Is what you're saying. This is the plot that we were doing, and we could say, let's call this thing plot penguins. So I'd go function df, put that in there, right? And then from there, now I could just actually pull all of this out, and I could call plot penguins. Right? That does the exact same thing. So that can be a very nice way to do it as well. There are some trickiness to creating functions that plot with ggplot and with working in the tidyverse generally with functions. So we'll have an entire lecture on that. Well, not on that, about half a lecture on that. It's called non-standard evaluation. And it really makes working with the tidyverse a lot easier, but it makes programming with the tidyverse quite a bit more difficult. So in some simple cases like this, where you're just passing the data frame to be plotted, it's fine. It's not a big deal at all. But if you instead wanted to have a common data frame, but be able to swap out the different columns, like the X and the Y axis, then it's going to be much more complicated. So just as a real quick example, we could just go like X, Y, right? And pass these as additional arguments. And so we'd go plot penguins, and you would expect that we could do like plot penguins and go penguins as the overall data frame, right? And then bill length millimeters, bill depth millimeters as the X and the Y, right? But notice it doesn't work. It says bill length millimeters not found. And that's because these are being passed as bare names. And so what you have to actually do is quote this input and then evaluate it in the right spot. So a very simple fix, just as a way of foreshadowing for things we will do, is when this is again a pretty simple example, but you can just surround each of them in double curly braces like that, and then it should work. Okay. So we will talk about all of that more in the future, but just know if you're trying to write functions with, and this goes for all of the tidyverse, all of dplyr, everything. They use non-standard evaluation prolifically, and it absolutely makes it easier to work with interactively, but it can make programming a little more difficult. Okay, so just be aware of that. Okay, now we're going to extend this even further, okay, to say, all right, now we've got these separate plots, we're going to write them all to disk. Okay, so we're going to save all of these plots. Okay, so that means if you think about the saving function, we're going to have to loop through two different things. We're going to have to first create a vector of file paths that we're going to use to save, and then we're going to have to loop through that. But then we also have to loop through our plots. So we have our plots that we created. We need to loop through those, tell it which plot to save, and then we need to give it a path for each of those plots as well. Okay, so if we were going to do this through functionals like lapply, this would actually mean we would be jumping in parallel iteration, which is Still, I think not next week, but the week after that. Okay, next week is introduction to per, and then I think the week after that is parallel iteration. So we're going to wait on that and not do that yet. Instead, we're going to use a for loop for that part of it. Okay, because it's easy to pass I multiple places, right? Or whatever. So we can do it with for loop. So we're going to do that. Okay. So first, we need to take our plots that we had, and we're going to save them all as an object. Okay, so coming back here, I'm going to pull this out of here again. Get rid of all this. And then I'm going to go function df. And then instead of this, right, let's see, what were they? It was fill length and body mass. Okay, so I'm just going to put that there. Okay, make sure that that works. It does not. Okay, so what is wrong here? I'm missing a parenthesis there. Okay, so that works, but this is just printing them to our screen. So what we're going to do is we're going to save all of this in a thing which I'll call, you know, penguin plots, whatever. You could call it whatever you want to call it. But we're going to save that all in a list. So like if we look at this now, str penguin plots, you will see that it's this list, and it's like a pretty big long thing because it's all the basically directions on how to draw this plot. Okay, plus some data and all sorts of stuff. So that's our plots now. And then we need to create our file paths for these. Okay, there's lots of different ways that we can do this. But one of the ways that I like to do this is by first creating a directory for my plots. Okay, so you could use base things for this. I'm going to actually use fs, library fs, which is that file systems one. I haven't introduced it yet, have I? I was thinking I did last term, but I did not. So that's fine. But from fs, we have this dir underscore create. And that is similar to the base function dir dot create. The one difference is this will only create one directory at a time. Directory is the same thing as a folder, right? Whereas dir underscore create from fs will allow you to create nested folders. Okay, so I'm going to say go here, create a folder called plots, and then inside of plots, say penguins or whatever, right? So I do that, and you can look at my files now. This was a different project entirely, but that's okay. So you can see I have this plots folder, and inside of that, I now have a penguins folder. Okay. Now I have the directory. Now I'm going to create names for all of the files that I want to write out. Okay. So what's my names of penguins plots? Let's look at that. Penguin plots. Okay, Adelie, Chinstrap, and Gentoo. These are the different penguins that we have plots for, right? So what I'm going to do is I'm going to say paste 0. So I'll call them file names, or just files. How about files? I'm going to paste 0. Those names dot however we want to say them, PDF. Okay. So now files just looks like this: Adelie.pdf, Chinstrap.pdf, Gentoo.pdf. But that's just a file. What we actually want is the full file path, right? So then I'll say file paths, and I'm going to say here, plots, penguins, and then just files on the end of that. Okay. And when I do that, you'll see I get these file paths. That's the full file path to plots penguins Adelie.pdf, plots penguins Chinstrap.pdf, and plots penguins Gentoo.pdf. Okay, is that clear? Questions on that? All right, now I'm going to write a for loop to save all of these plots. Okay, we'll revisit this in the slides after I do this. All right, so I'm going to say for, I'll say for plot in seek long file paths. There's lots of things you could seek along here, right? It doesn't really matter. For each of those, I'm going to say ggSave. And notice the first argument in ggSave is the file name, right? So I'll say file paths I, except it's not going to be I, it's going to be for plot, right? I'm going to do this like this. So give me the file path for the plot. And then the second thing, so let's actually just pull up the help documentation here. The second thing for ggSave is the actual plot that you want to save. Okay, so that's where I will then say penguin plots plot. Okay, and then from there I could put additional arguments like width equals 6.5 and height equals 8. Okay, those are in inches by default. Okay, so then I run that and oh, right. Yes. So I messed up because penguin plots is a list. So I need to do double brackets on that to say, give me the actual plot, not give me the list that has the plot in it. Okay. So I do that. Notice it's giving me the messages that it's drawing. I go to my files and there they all are now. If I go to my local, we could see them better, but those of you on Zoom will not be able to see them as well. Plots, penguins, and there you go. 1, 2, 3. Okay. All right, let's go to the slides and we'll walk through it again on the slides. Okay. So we're creating our plots and we're saving them to this plots object that is a list with each plot in it, right? And we know it's a list because we used lapply. So that's always going to return a list for us. Then we're going to create some file names. Okay, so I'm doing this with the empty cars one. So I'm saying here plots, and I'm just creating, I don't have this nested one like I just created, right? It's all, I'm putting them all in the plots folder. I'm going to paste 0 sil and the names of bysil and .png. So I'm saving these as a ping. I did them as a PDF when I was saving them, right? But either way. And then when I look at file names, it's the full file path and it gets cut off here, but you should see the actual different names of bysil. So 6 or 4, 6, and 8. Okay. So sil4.png, sil8, 6.png, and sil8.png. Okay, and then here is exactly what I just did, right? I even use the same width and height. That's funny. You shouldn't actually have to specify the device. It should pick it up on its own, but if you want to be very careful about it, you could. But I'm going to say the file names, and that's an atomic vector, so I'm using a single bracket, and then plots, that's a list, so I'm using a double bracket, and then additional arguments to ggSave. Okay, so again, this is like a super powerful framework if you think about it, if you're doing any sort of operation at scale. So for example, if I wanted to, let's say I was working with one singular school, right? And I wanted to create some plots for that school. I could do it without doing any of this. But then what if I get 5 schools? Well, then I can copy and paste 5 times. I guess it's not that big of a deal. But then what if I get every single school in the state? That's going to be really hard to scale at that point, right? But by doing it this way, the code for one school is the same as for 5 million schools. It doesn't matter, right? It'll take longer to run, but the actual code that you've written will scale, right? It doesn't matter how many observations you have, how many times you're doing it. The code is going to be the exact same. So it's super powerful because this is, I would argue that this sort of an approach, this functional programming sort of an approach, is the thing that in my career in educational research anyway, has like made people be like flabbergasted with what I've done for them more than anything else. Because it's just like, they ask for something and it's like, bam, I get it right back. And it's like, boom, tons of stuff, right? And it's exactly what they want. And it's a bunch of it. And it's all really nice and whatever. And it's all from this approach. It also has great benefits in terms of debugging, because if there's an error anywhere, there's going to be an error everywhere. And so then you only have to find that error in that one spot. Whereas if you're doing a copy and paste thing, you could have an error for one of them, but not for any of the rest of them. And that's going to be really hard to find, right? Okay, we're not going to do that part. We're just going to continue on, so we can get to make sure that you have enough time for the lab. Okay, let's say instead of just by one group, with dplyr group by, you can group by multiple things. So maybe we want to group by multiple things too. If we want to do that, you can do that pretty easy. All you do is in the split argument, instead of just passing the one thing to group by or to split by, you're going to pass two things, but you pass it to the two things within a list argument. Okay, so I'm going to split penguins by species and island, but I pass species and island in as a list itself. Okay, and then this looks like this, Adelie.bisco, right? So this is all the data for species Adelie and island Bisco, all right? And then this is all of them for species Chinstrap, island Bisco. Notice there's none, right? There's 0 rows in that data frame. Now we can loop through this if we wanted to and create some plots. It's not any more difficult. And we can look at the first few, right? There's 1. There's 2, right? There is nothing on 2. So 1, 2, 3. So what we probably want to do is not produce plots like this, right? That's not very helpful. So what we probably want to do is take that split object and remove any of them that have no rows, right? So how would we do that? Here's how. Okay, we're going to first look through that list, and we're going to create a logical vector that says, are there 0 rows, right? And ideally, we want this thing to be back to return to us as an atomic vector, right? So we don't want a list in return. We could, but an atomic vector would be better, right? And it would be best if it was just trues and falses, logical, right? True, it has 0 rows. False, it has more than 0 rows. Okay, so we'll do that in a moment. What that is all prelude to are these variants of lapply. Okay, as I mentioned, lapply will always return a list, and that's really helpful because we know for sure what we're getting back. So that's called type safe. Okay, we are certain that of the type of thing that is returned. But many times, like in that example I just showed you, you don't actually really want a list back. You want an atomic vector back, or you want something else back, right? And so that's where these variants can help. sapply is the simplest solution. The S in sapply stands for simplify. And so what it will try to do for you is it will take your output and it will try to simplify it for you. Okay, so this is totally fine for interactive work, but I strongly recommend against it for programmatic work, because when it's doing that simplifying step, it is super unpredictable. Okay, so just like lapply is very type safe and very predictable, sapply is the opposite. Sometimes you will get an atomic vector. Sometimes you will get a matrix. Sometimes you will get an array. It just depends. And sometimes you will get a list. Okay, so you could get a list, you could get a vector, and an atomic vector, you could get a matrix, or you could get an array of however many dimensions. Okay, so again, totally fine for interactive work, not so fine for programming. bapply is the alternative to sapply that works the exact same way, except you tell it how to simplify. Okay, so bapply is more verbose. You have to write more code to get it to work. It's also not, I would say, the easiest function to use in terms of just like being clear what you're asking, how to write it to get it back how you want it to be. So that is really what PER helps solve a lot of, is making VApply a lot easier to work with. That's one of the main things that PER helps with, okay? But VApply is a great function. I use it all the time. And basically it's just like sapply, except you specify the type of output. So I would argue if you're going to be doing interactive work, nothing wrong with sapply at all. If you're going to be writing functions, so more programmatic work, VApply should always be preferred. Okay. All right, couple of examples. When we do that same, this is the exact same simulation we've done a bunch of times now, right? 10 observations from a random normal distribution with a mean of 0 and a standard deviation of x, where x is these increments from 1 to 5 by 0.2. Okay, I do that whole thing in one line of code, and what I get back is this giant matrix. Okay, and so again, this is pretty nice. We get 10 rows and 21 columns. Okay, so each column is a new each column is a new set of 10 observations from the corresponding distribution. Okay, but notice how I had to sit there and think about it for a second, what rows we're representing versus what columns we're representing. Okay, so that's a little bit tricky, but it is nice to just instantly have it returned as a matrix for you, right? Another example, sapply penguins is.double. Okay, so we're looping through the penguins columns and we're calling is.double, but instead of getting a list in return, we're getting this logical atomic vector in return. Okay, so this is much nicer to work with than the list of the same thing. And from this, we can now use this for other purposes like subsetting. So for example, here's all of penguins, right? And then in this line, I'm saying, okay, loop through penguins and see if it's double or not, and give me only those columns in return. And I get back this subset data frame where I am now programmatically pulling the columns, right? I'm pulling the columns based on whether they match a specific type or not. Okay, so just a very quick challenge, 2 minutes. This is looping through and pulling the columns that are of type double. What I'd like you to try to do now in 2 minutes is the opposite. Return all the columns that are not double. Okay? Give it a try. Okay. This is how I did it. There's more than one way to do this, but basically, anytime you're using the exclamation point, it's just going to reverse the logical that you have, right? So back here, this is returning all of the ones that are of type double, right? So like when I do this, it gets false, false, true, true. If I just put an exclamation point in front of that, all the falses become trues, all the trues become falses, right? And so that's what I did here. Just put the exclamation point in front of the sapply. Okay, there are other ways to do this, so you may have been successful with a different way, but this is how I approached it. All right. So on our last one, right, we had those plots that were empty. Rather than having you try, I'm just going to do this myself. So first of all, we need to do, I'll just call it split 2, right, where we're going to split penguins, split penguins by list, penguins species, and penguins island, right? Now, when we do this same sort of, not that one, when we do this same sort of looping, I'll call it penguin plots 2. And I'm going to loop it by split 2. Okay. Then when I look at penguin plots 2, 1, that should be fine. That should be fine. But then the second one is empty. Okay. So the question is, how do I remove these empty plots? Right? Any ideas on how I would do that? And I'll give you a hint. It shouldn't be on the plots that I'm removing. It should be on the data that I'm removing. Right? So how do you think I'm going to do this? Any ideas?
Once you split it, see what doesn't have to do.
Good. So here's my split 2. And what I can do is I can go sapply split 2 in row, right? That's going to give me all of the number of rows for each of these. So I could do a couple of different things. I could say function df, and then I could say in row of df is greater than 0, and that will give me a true false back. Or I could actually just take what I had before, which was just in row here, like that. And then this is already a vector, so then I could just say greater than 0, and that would also work. Okay, so then when I create this next plot, I could take either of these. This one's probably my preference, but either way is fine. And I'm going to subset the list based on this logical. Okay, so I'm going to pull this out of here though, because that ends up too much. So I'll call it plot, or I'll call it two plot. Okay, and we're taking split 2 and we're subsetting it based on this logical vector. Okay, so we're going to keep this one, but we're going to drop that one. We're going to keep this one, keep this one, keep this one, drop this one, keep, drop, drop. Okay, so we do that, and then now we're going to loop through to plot instead. And notice now I could just plot all of these, and they're all going to be good. Right? Questions on that? Okay. So here it is again. Same way I just did it. And then we just say we're going to keep those ones. Then we do our plot. Okay, there's the first one, there's the second one, there's the third. Okay, so you can probably see now from sapply that simplifying can be really, really helpful. However, as I said, sapply is also very regularly unpredictable. And so it's not very good for programming. And you will absolutely see people using sapply inside of functions. There are certain cases where you can be certain of the output that it's going to give you. Even so, I would recommend never doing it, okay? Because it's just not a good practice to get into. vapply is going to be much safer, okay? But, so I've already done that. vapply solves this issue, okay? So what vapply does is it simplifies how you tell it to simplify. So that means it has this additional argument, fun.value, okay? Fun.value is a required argument for vapply. It must be supplied. And what it does is it asks you how you want the result to be. If it can provide it in that result, it will. If it cannot, it will throw an error, okay? So you would never really have list over here because then you would just use lapply, right? So what you're going to do instead is give it the atomic vector type that you want, and then you're going to give it the dimensions that you want. And for me, I would say 99% of the time, that's just going to be 1, okay? Because I just want an atomic vector in return instead of like a matrix. But if you want a matrix, you can actually supply the dimensions there and it should work. It's a little tricky. I've had issues with it in the past, but if you work with it long enough, you can figure it out. Okay, so loop through empty cars, for example, and give me the mean. And then the output that I want is double. Okay. So I say double of dimension 1, basically just a single line. Okay. An atomic vector. If I go penguins is dot double and I say character, then I get an error because it's providing back a logical, and then, but I asked it to provide back a character. And so I get an error. Okay. So if instead though, well, so this one is a little bit different. In some cases, it will coerce, right? And it's not exactly clear to me why it doesn't coerce to character, but it does coerce to logical. So I don't exactly know why that is. Maybe I did know at one point and I've forgotten. I don't know. But sometimes, so like in this case, I'm saying is dot double. Oh no, sorry, that's not coercion. That's why. Is dot double is a logical, right? And then I'm asking for a logical back. I still do think there are some cases where it will coerce though. Yeah, so there you go. If it can coerce without a loss of information, then it will sometimes, except this shouldn't be a loss of information either. So that's not always true apparently. But so here's an example. Is dot double, that's a logical, right? But then I'm requesting of type double back. So the trues get turned to ones and the falses get turned to zeros. Here's another example where I'm going to loop through air quality. Okay, so I'm looping through air quality, and for each column, I am going to sum the missing values. Okay, and then I'm saying what I want in return is double of 1. Okay, so again, for me, 99% of the time, this is just a 1. Okay, and so we get ozone, solar R, and they get 37 and 7, and the rest are 0. You could do the same thing with sapply, but again, it's less safe. So this is great for interactive work, but not for programming. Okay, so summary for our loops, and then we'll get to our lab. Okay, so we have about 50 minutes still left of class. So you probably have about 45 minutes by the time we get through these last couple of slides for the lab. Okay, so for loops are super flexible, and in some ways they're better than functionals in what we've introduced so far anyway, because you can, you know, say for I in whatever, and then you can put I 17 places in there if you want to. And so like when we saw with saving the plots, it was easier to use a for loop than to use elapply. Okay, there's also absolutely nothing wrong with them. Okay, the big drawback to them is that it's a lot of code to write for a single loop, and elapply is much less. And so if you're doing, say, 7 loops in a row, then it's going to be a lot more code to write a bunch of for loops, and you're more likely to introduce errors that way than if you write elapply or sapply or vapply or whatever. So that's exactly what that says. More text, often repetitive text, and so that can lead to errors and bugs. Flexibility is also always like a blessing and a curse, right? It's good to be flexible, but sometimes that can lead you down avenues that are really not the best way to do something. So elapply puts the focus on the function and the thing that you're iterating through, right? So that's a plus of them. They will, elapply always returns a list, which is great. And sapply will try to simplify. And then of course, vapply is strict and requires a given type. Okay, really quickly on apply. Apply is, I've never really lectured on apply because I think it's useful and I use it a fair amount, but there are also always alternatives to it. But I just decided to do it this time because I still like it. And so you can think, you know, we can go through these slides and you can decide if you like it too. And if you do, great. If not, that's fine. All right. But basically, you're going to apply X, and X is like the thing that you want to loop over. And then the second argument is the dimension, okay? So 1 means you're going to loop over rows, 2 means you're going to loop over columns, and 3 means you're going to loop over the matrices if it was like a nested, like an array where you have essentially a bunch of matrices that are layered on top of each other. And then 4 would be through the 4th dimension, whatever, okay? So it just goes on from that. And then you pass the functional arguments, okay? So here's a very quick example where we have a data frame that has some people, right? We have their first name in the first column and their last name in the second column, okay? And so we might want to create a new column that is the first and last name of these people, okay? So we might try something like this, where we'd say full name is equal to paste first last and collapse with a space. But we get this in response, right? Frederick Douglass, Anna Murray, Julia Griffiths, okay? All of them, the whole thing goes into each thing, right? And that's because when we're doing paste, we're actually getting this entire column and we're trying to paste that with the entire second column, okay? So we don't want to do that. We want to do it by row, okay? So instead, we can do it with apply, where we say apply people, the thing we want to loop over, to the first dimension, the rows, right? And apply the function paste with collapse equal to a space, and we end up with the names as we would expect, okay? So that can be done within a mutate call, just like we had before, and it works just fine, right? So we go people mutate full name is equal to, and then we put our apply code, and now we get a new column for their full name that is more how we would expect, okay? So anytime you're wanting to do something by row, there's a bunch of different options. This is one of them. It's not always the most efficient, but I find it to be actually pretty clear in terms of what's going on. Other people don't like it as much, so again, it's up to you. Okay, for columns, here's an example with columns, right? I'm using the air quality data set. I'm looping through the second dimension columns, right? And I'm applying this function x, where I'm just saying as.numeric scale x, okay? So it's going to scale x, and then it's going to call as.numeric on it, and we get this in return. Okay, there are also other loops like tapply. I don't think it's very important. It's the same as doing lapply split, okay? It can be a little less code, but it's also a little less clear what's going on. So yeah, all of this takes practice. I've said a couple of times, I would really try to avoid nested loops. I think they're gnarly and they're not fun to debug. Okay, so that's an introduction to looping. This is the first of multiple lectures we will have on looping. Okay, so hopefully you're not feeling totally overwhelmed. We have the rest of the day for the lab. So we will have, after I go over this, about 40 minutes for it. Okay, you are welcome to work in groups, and I encourage you to work in groups. Okay, and then I will kind of be hanging around, and I will walk around a bit, but please do ask me for help if you want. Okay, if you're getting stuck at all, ask me for help, and I'll come over and I'll talk to your group and help you get unstuck. Okay, but this lab has two different sections. The first is on data structures, which was mostly the last lecture, right? So I'm asking you to just run this code. Okay, so you can just copy and paste this code. And then from here, from the model results, which is M, right, from this thing, I want you to extract the QR tolerance, which is called tol. Okay, so that means you're going to have to dig into that model object and find that thing first, and then you're going to have to extract it. Then extract the term labels from the model. Okay, the term labels. This is a little bit difficult also. And just as a hint, it involves pulling an attribute from an attribute. Okay, So one way you could do that is pull the attribute first and then inspect that thing and then pull the attribute from inside of that. Okay. And then from L, so here's the first one is all about M. Okay. From L, this is a nested list, right? We have A, which itself, so this outer list is of length 2. It has A and B, right? But A itself has a list. One inside of that is M, just like up here, but this is a different M, right? And it's a matrix with 3 columns, okay? It also has V, which is a vector of 1 to 7, and then B is a data frame with 2 columns, okay? So from L, you're going to use at least 2 different methods to extract M. So to get this out of the list, at least 2 different methods, okay? I'd also like you to extract the 3rd column from the matrix and importantly, maintain the dimension structure, okay? I've had lots of people do this in the past where they call as.matrix on it after they've extracted it. That's not what I'm looking for, okay? There is a way to pull this while maintaining the dimension structure, okay? Then finally extract the score for student 7. So notice there are 15 students. I want you to extract the score for the 7th student in the data frame. Okay, so that's the data structure part. Then on the loops, I want you to read in the insurance coverage.csv, which if you have cloned the repo should be in the data folder. I sent out an announcement about this, but the data, I actually used to use this as like a sort of tricky thing. It's difficult to read in, or at least it used to be. But Readr, the Readr package, has basically fixed everything for you. So it's really easy to read in now. So just use Readr and then use read_csv to get that file in, and you shouldn't have any trouble. Okay. Then you're going to split the data file by age bucket and sex name. Okay, so that's the first part. Then you're going to use a for loop to calculate the mean healthcare population, so HCPOP, for each combination of the split that you've done. Replicate this calculation using lapply, sapply, and vapply. So you do it with the for loop first, then you do the same calculations with lapply, same calculations with sapply, same calculations with vapply, and then produce separate plots for each of those, right? And then use a for loop to save the plots to a folder on your computer. Okay? Any questions on any of that? Okay, please do work in groups and feel free to get started.